This is a transistor switching circuit. It's quite different from any vacuum tube switching circuit. The transistor itself acts as the switch. This kind of circuit is seldom used for such simple jobs as turning on lamps. It is used very frequently to perform mathematical operations in electronic computers. This film shows some elementary principles of transistor switching in computers. The basic characteristic of a switching circuit is the fact that it has only two possible operating conditions. Here, they are on and off. But any two-state circuit is called a switch, even though it may not be a simple on-off switch. This one has two different voltage outputs. And the other condition, the digit 1. Of the 10 digits, only 0 and 1 are actually used in computer design. Therefore, only simple two-state switches need be used. In the off condition, the output can represent either 0 or 1. The choice is arbitrary. In the on condition, the output, of course, will represent the other digit. This simple switch, used in various combinations, can perform mathematical operations. However, even elementary mathematical operations are too complex to be performed in one-stage electronic circuits. So the operations are broken down into steps. This circuit performs one such mathematical step. It is called an OR circuit because it delivers an output if either input A or input B is present. Here's another example. This is called an AND circuit because it delivers an output only when both input A and input B are present. The circuit consists of two switches in series. When both inputs are negative, current can flow in the load. If either input is positive, the corresponding emitter is reverse biased and the circuit through the load is interrupted. By using such combinations of switching circuits as this and this, complex computer systems can perform in seconds mathematical computations far too difficult to do at all with pencil and paper. Let's see how one switch works, since it's used as a basic building block for constructing computers. The collector output is controlled by voltage applied between the base and emitter. When the input signal, battery voltage here, is applied as forward bias, current flows in the collector circuit. The switch is on and there's an output. When the input signal is reversed, the emitter is reverse biased, so there is no current flow. The switch is off. Though it looks like one, this is not a common emitter amplifier. It's a direct current switch. When the switch is on, the IR drop across its load cancels the collector's reverse bias. With no voltage across the collector junction, the transistor itself uses up almost no power. When the switch is off, there's reverse bias on the emitter junction, and without forward emitter current, no current can flow through the collector. With no current, no power is consumed. So, whether the circuit is on or off, there's no power loss. It's practically a loss-free switch, as efficient as a knife switch. In the on state, when the voltage at the collector junction is 0, the collector current depends only on the collector battery voltage and the load resistance. The collector is in a state of saturation. It can draw no more current, no matter what the emitter may do. Under these conditions, practically no power is lost in the transistor. However, the response of the circuit shown here may be undesirably slow. To see why, let's replace the transistor symbol with a cross-section of the transistor crystal. In the base, most of the holes arriving from the emitter move on to become the collector current. Because the collector is saturated, it can't accept all the holes. The remainder eventually combine with electrons in the base to sustain the base current. They are minority carriers in the base, however, moving only because of their own thermal agitation. So it takes them a while to meet electrons, and quite a number of them accumulate in the base. This accumulation is called minority carrier storage. Minority carrier storage causes most of the problems associated with transistor switching. When the input voltage is reversed to turn the switch off, the forward emitter current stops at once, but the collector current is likely to continue for a brief interval, sustained by the stored carriers. Thus, the switch is a little slow to respond. There is also a brief delay when the switch is turned on due to the transit time, the length of time it takes the carriers to travel through the base. The collector current cannot reach its full saturation value until holes are arriving in adequate numbers. To make the switch respond more quickly, the circuit is often arranged like this. The input resistor limits the emitter current so that just enough carriers enter the base to keep the collector saturated, with very few left over to become stored minority carriers in the base. When the switch is turned off, there are few stored holes to maintain the collector current, so it stops very quickly. The capacitor functions to make the switch respond quickly when turned on. It's a low impedance path for the rising input current, so it momentarily bypasses the input resistor to provide a large starting current. This produces a surge of carriers into the base so that enough are available almost immediately to produce maximum collector current. This is a basic switching circuit, a fundamental building block for computers used in many ways to perform mathematical operations. This common computer circuit is also a basic switching circuit. It is a trigger circuit, commonly called a flip-flop. It's a simple arrangement of two switches with their bases and collectors cross-connected. Only one switch functions at a time. It gets its emitter to base forward bias from the reverse bias on the collector of the other transistor. The first transistor's collector voltage is 0 because the collector is saturated. Applied through the cross connection, this 0 voltage keeps the second transistor's base at ground potential. With no potential between its emitter and base, the second transistor cannot pass current. Switch 1 will deliver an output indefinitely until a negative input is applied to switch 2. As soon as transistor 2's base becomes negative, it conducts. Current flows in its collector, which reduces the collector potential to 0. With 0 volts applied to its base, transistor 1 no longer has forward emitter bias, so it stops conducting. Its collector again has reverse bias, which serves as continuing forward bias for transistor 2. Transistor 2 continues to deliver an output even though the input signal is no longer present. This is, of course, a two-state circuit like the simple switch. But this one is bistable. It will remain in either one of its two stable states indefinitely until an incoming signal makes it flop over to the other state. Circuits like those shown in this film, combined in various ways, make possible completely transistorized digital computers.